Good morning and welcome to our lesson today. We are still on heat and we still want to find out what heat can do for us. Now, the last time we looked at latent heat, where we discovered that when matter is changing from one state to another, we need some heat to be absorbed by matter. But that heat, once it is absorbed, we do not necessarily realize change in temperature. Today we want to find out how can we be in a position to quantify latent heat and probably how it is going to affect our calculations of specific heat capacity. Just to bring you to speed, we said that latent heat is that heat needed to change state of matter without change of We said that latent heat is that heat that we are going to need in order for us to change the state of matter without realizing change in temperature. Now, we agreed that we have several states of matter. We could talk of a solid, a liquid, gas. Sometimes we even add a substate that we call plasma. Plasma is a substate of matter where molecules exist. Gas exists as molecules and ions. Now we have plasma as a substate of matter where you can heat gas so that now some molecules will be ionized, and we can have that state where we have a mixture of molecules as well as ions. Now, when we want to navigate through the states of matter, we could talk about several processes. Let us assume that this is our solid. Again, we have our liquid here. And finally, we have a gas. Now, to change from solid to liquid, we call that process melting. And melting requires that we have some effect of heat being absorbed into that solid for it to be in a position to transform to a liquid. We can as well talk about changing a liquid to a gas in a process that we call vaporization. We can go through the rivers of the processes where now we can talk about condensation. And finally, from liquid to solid, we can call it freezing. Freezing, or what we call solidification. Now, all these processes will involve change of state. They will involve change of state, which means the heat that is absorbed by matter to transform from one state to the other is what we are actually interested in. You could also look at a direct process from a solid to a gas, which we called sublimation. And you can also change a gas to a solid in a process that we call decomposition, or even some books will still call it sublimation, decomposition, or even sublimation. Now, those states and the changes thereof are what we are going to be discussing in this lesson. Now, let us look at types of latent heat. Types of latent heat. Types of latent heat, and basically we have two, where we called one latent heat of fusion, and the other one is the latent heat of vaporization. Latent heat of fusion and latent heat of vaporization. I will want us to expound on each of them, and we start with latent heat of fusion. Let us start with latent heat of fusion. And latent heat of fusion is actually that heat that will be required to change a given mass of a material from solid to liquid without change of temperature. That you can be able to change some given mass of a solid into a liquid without change of temperature. Now, we agreed that this latent heat is actually needed to break the forces between particles of matter. So we ask ourselves, do we only talk about change of state from solid to liquid? How about the reverse? Now, that brings us to the next concept, that latent heat can either be absorbed or released. Now, when latent heat is absorbed, absorption of latent heat brings about breakage of forces holding particles of solid together. So now you could be, after making the particles of a solid actually gain more speed or even move faster, you excite them by giving them this heat that we are talking about, which we are calling the latent heat. What now happens is that it breaks the forces between the molecules. Remember that matter is made up of particles. Now in a solid, particles are closely packed. Particles are closely packed. Particles are closely packed, and we say that movement is only by vibration. Now, they are held together by strong covalent bonds. Or we can call them strong intermolecular forces. They hold the particles of solid together. Now we want to change this solid into a liquid, which means what we are supposed to do is to break the forces, these forces holding the particles together. We are supposed to break them by supplying heat. That way, the particles are now going to be moving at random, because the forces will have been weakened by the heat that we are calling the latent heat of fusion. Now, how about when we want to change a liquid to a gas? When we want to change a liquid to a gas, remember that particles of a liquid are they have moderate spaces between them, and that's why we say they can move randomly, because they have small spaces between them, and thus they collide. They constantly collide. Now, we have already weakened the forces in order for us to resort to a liquid from a solid. Now, we want to rebuild the forces so that now the particles will not be moving randomly, but rather they will reduce the movements to vibrations, because there is actually no space for them to move, and again the forces will have strengthened again, which means for us to rebuild the forces of a liquid, in order for us to get a solid from it, we need to lose. We lose latent heat of fusion. So you could either talk about absorption or even loss of latent heat. Either way, latent heat of a substance will always remain constant. Now, let us look at a graphical representation. Graphical representation of the change of state of matter. Graphical representation of the change of state of matter. We can plot temperatures in degrees Celsius against time in seconds or whatever units. But remember for you to be safe, it is always commendable to work with, it is always advisable to work with SI units. Now, we want to heat a liquid, or rather we want to heat a solid, for example ice, from some negative temperature through the melting point to some temperature above the melting point. Let us start from -10, for example. Now, we say that when we heat ice, its temperature is going to increase up to the melting point. Now here we are going to heat it and realize that there will be no change in temperature for some time, and then after all our ice is melt, now again temperature will continue to rise. Now at this particular point here, we are changing state. Here we realize change of state of the ice, now from a solid to a liquid, or rather you could talk about melting at this point. So it doesn't mean that because there is no change in temperature we are not supplying heat. It's actually absorbed, but there is no change in temperature simply because we are changing state, and the heat involved is what we call the latent heat. And after all the ice is melt, now we again follow the normal temperature rise curve. Now let's go specific and talk about specific latent heat of fusion. Specific latent heat of fusion. Now we have agreed that for us to change a liquid to a solid, or even a solid to a liquid, we will need some heat we call latent. Now how about that heat which we will need to change a unit mass? A unit mass. That is what we call the latent heat of fusion. It's the heat required to change a unit mass of a solid into a liquid without temperature change. Now we want to talk about a unit mass. It's not just a given mass, but now a unit mass. Now, we know that heat is given by mass, specific heat capacity, and now the change in temperature. But now we cannot apply this formula because here our change of temperature is 0. So right now we talk about latent heat of fusion, and we multiply that by mass, which now brings us to latent heat of fusion being equal to heat divided by mass. Because we are talking about a unit mass, we have to take care of that. Now, the units. Again, we ask ourselves, heat is measured in what units? The joules. Joules. And mass is in kilograms. Therefore, latent heat of fusion is given in joules per kilogram, or joules per kilogram, like that. We look at an example involving latent heat of fusion, an example or two. We look at an example or two. Now the question reads, in an experiment to determine latent heat of fusion of ice, 0.025 kilograms of dry ice at 0 degrees centigrade is melted up in 0.2 kg of water at 21 degrees centigrade in a copper calorimeter whose mass is given as 0.25 kilograms, and the mixture falls to a temperature of around 11 degrees centigrade. So we are required to calculate the latent heat of fusion of ice. Now, let us pick up the information we have been given in our question. We first talk about the masses. Mass of ice is given as 0.025 kgs. That of calorimeter is given as 0.25 kgs. Mass of water is given as 0.2 kgs. Now, specific heat capacities, that of water is given as 4,200 joules per kilograms per Kelvin. That of copper is given as 400 joules per kilogram Kelvin. Now, temperature change of ice is from 0 degrees centigrade to 11 degrees centigrade. That of water is from 21 to 11 degrees Celsius, and that of the calorimeter is also from 21 to 11 degrees Celsius. Now, this one will be 11 degrees centigrade, this one will be 10, and this one is also 10 degrees Celsius. Now, what we know is that heat gained by ice is equal to the heat lost. Heat lost by the calorimeter plus water. Probably we can start by looking at the heat lost. Heat lost, and the heat lost will be mass times the change in temperature and times the specific heat capacity both of water plus that of the calorimeter. Now, let us substitute in the equation. The mass of water is given as 0.2 kilograms. We add that to the change of temperature, which is 10 degrees centigrade, and we multiply by the specific heat capacity. And this one is going to be added to that of the calorimeter, which is 0.25 kilograms times 10 as our change of temperature times the 400 that we were given as the specific heat capacity. That gives us 8400 joules. We add to 1000, and the heat lost adds up to 9400 joules. That is actually the heat lost by both water and the calorimeter. It is given by mass times the change of temperature times the specific heat capacity of each of our items of consideration, and we add them together to get 9400 joules. Now, our 9400 joules is the heat lost. Joules. Now let us look at the heat gained by ice. We have been told our ice is 0.025 kilograms by mass. So now will be the latent heat of fusion plus the heat to raise the temperature from 0 degrees centigrade to 11 degrees centigrade. That is the much our ice has gained. Now, the latent heat of fusion is given by mass mass. Now, because this is specific, we multiply by latent heat of fusion of unit mass so that we can get the total. Then we add to the mass multiplied by the specific heat capacity of now the melt ice and the change of temperature. Here the mass has been given as 0.25 kilograms. We multiply by the latent heat of fusion, that is what we are looking for. And this one we add to mass, the product of mass, specific heat capacity of water, and now the change of our temperature from 0 to 11 gives us a positive 11 degrees centigrade. Now this gives us the total of the heat that our ice gains. So here the heat gained is equal to 0.025 plus 1155 joules. Now, but heat gained is always equal to the heat lost. So we equate 9400 joules to our heat gained. and we can collect the like terms, so that now 0.025 multiplied by latent heat of fusion is equivalent to 9400 subtract 1155 joules, which gives us 8245 joules. Then we can divide rho out by 0.025, so that now latent heat of fusion of ice is 329,800 joules. 329,800 joules. That is our latent heat of fusion of ice. We could look at another example. Now the question reads, 50 grams of molten wax at melting point of 62 degrees centigrade was poured into a calorimeter of mass 40 grams with 80 grams of water at 15 degrees centigrade. That after stirring, a final temperature of 44 degrees centigrade was actually realized. Now with that information, we should calculate the latent heat of fusion of wax if its specific heat capacity is 600 and that of the calorimeter is 400. Also that of water is 4200 joules per kilogram Kelvin. Now Let us look at what we have from the question. We have the masses. We have the masses. The mass of water is 80 grams. Mass of the calorimeter is 40 grams. That of wax is 50 grams. Now, we could also compute the changes in temperatures for water. It changes from 15 to 44, a difference of around 29 degrees centigrade. Same case applies to the calorimeter, also changing by 29. We also now have our molten ice, whose temperature is dropping from 62 to 44. So now the change of temperature of the wax is (18 degrees centigrade). We also have been given the specific heat capacities. Specific heat capacity of the wax is 600 joules per kilogram Kelvin. That of water is 4200. And that of the calorimeter is 400 joules per kilogram per Kelvin. Now let us try and come up with the latent heat of fusion of our molten wax using the information that we have been given. Now, always recall that heat gained is always equal to the heat lost. Remember that heat is actually a form of energy, and by the law of conservation of energy, we cannot create or even destroy energy, but only transform it from one form to another. Now, heat gained is being gained by water and with the calorimeter, and the heat lost is by our molten wax. Let us start by heat gained. Will involve computing the heat gained by water. Heat gained by water plus the heat gained by our calorimeter. We could change the masses to kilograms, so that now here we have 0.08, 0.04, and 0.05 kilograms respectively. Now, let us substitute what we have in the equation, so that now the mass of water becomes 0.08 kilograms. Its specific heat capacity is 4200 joules per kilograms per Kelvin, and the change of temperature is 29 degrees centigrade. We want to add that onto the changes realized by our calorimeter, where the mass was 0.04 kgs. We add to the specific heat capacity, or rather we multiply with the specific heat capacity and also the change in temperature and also the change in temperature, whereby now (9,744 joules) we add to 464. That will be our heat gained. That is 9,744. We add to 464, which gives 10,208 joules. That is the sum of the heat that was gained by water and which was gained by our calorimeter. Therefore, heat gained will be 10,208 joules. Now we come to the heat lost. The heat lost, and the heat lost will involve the latent heat of fusion plus heat lost to drop temperatures of wax by 18 degrees centigrade. Now, our latent heat of fusion is given by mass, which is 0.05 kgs. We multiply that by the specific latent heat of fusion. That one we add to the product of mass, specific heat capacity, and the change of temperature. And the change of temperature. Gives us 540 joules plus 0.05 multiplied by specific latent heat of fusion. That one is the heat lost. Now, equating the two, we want to equate the two so that now we say heat gained, which is 10,208 joules, is equivalent to that which was lost, which is 0.05 multiplied by specific latent heat of fusion. This one we add to 540 joules. Then we can collect the like terms, so that 10,208 minus 540 will be equal to 0.05 times specific latent heat of fusion. And when we compute that, we get the latent heat of fusion as 193,360 joules per kilogram. 193,360 joules per kilogram. So basically that is all for today. In our next lesson we shall be looking at latent heat of vaporization and how we can be able to calculate it given a few parameters. Thank you.